I have homeworks to hand back to people. Let me do that. Corey's not here. Adam's here. I got the homework too. Okay. The rewrites. Melissa's here. I got rewrites for you. Dalvin's here. I got rewrites for you. John is not here yet.
He said he'll be here in a few minutes. He was helping students in the math lab. Yes, he was.
Thank you very much. Melissa's here, homework 3. Chuck is here, homework 3. Audra's here, homework 3. Dalvin's here, homework 3. Okay, so as some announcements. Let me remind you that test 1 is upcoming. So test 1 is on Wednesday. It covers all the material you have. Through the squeeze thing. I've given a study guide for this test. Is there anybody in here who would like the study guide? Who maybe had done? I send it out via email, but I've also been offering a hard copy of it. Does anybody need the hard copy? Anybody want the hard copy of the study guide? Okay. Okay, and then the other thing I want to do is I want to make one more announcement, and that is we had a study session on Sunday, but I'd also like to have a study session number 2. On Tuesday, in this room, from, let's see, from 6:15 to 8:15. Again, it's in this room. John, I had homework for you. Here it is. Thank you. Thank you. I'll give you that right. Today is dedicated to answering questions. Okay? And so you see here on the study guide that we have a list of definitions. We should know those. What problem 1 will be. Okay? So I won't, there's no use of trying to hide. I want you to know what to expect. Problem 1 on your test will be the following types. Okay? We'll say, give the definitions of the following. I'm not about to tell you which ones, but there will be 5. So 4 points each. And there'll be A, B, C, D, and E. So that'll be the first question. And it'll be 4 of those 19 things I'm asking you this on the sheet to know. Problem 2, it will say state the following. 5 points each. And I'm not sure, it will either be A, B, or A, B, C. Probably A, B. Probably just 10 points. Might be 15. So we're talking about 35 points of the test is, do you know these factual definitions and statements, okay? Then I will probably ask you 2 to 3. There will be probably 3 proofs that we've seen. Okay, something like that, okay? 2 or 3, let me write that down. Proofs that we've seen, something like that. Okay? And there'll be varying point values. If it's an if and only if statement, might be worth more than just if it's an if statement, okay? Something like anywhere between, well, let's say 8 points for one of these if-then type statements, or maybe 13 for a if-then, if and only if statement, I should say. So probably about, I don't know, let's say 20 points, 20, somewhere like that in that range, 20, 25 points, about that. So here is what I'm thinking. This is 20, maybe 10 to 15, somewhere around 25 points for this, 20, 25 points for this. Is that okay? So that's a good portion of the test. It's just things that you should know from the study guide. Statements, proofs, definitions. Then, I'm going to definitely ask you, so if you flip the page, I'm going to ask you to prove a sequence converges to a specific number. Okay? And that was like from homework 3. I'll ask you to find the sup of A or inf of A from a given set. It won't be worth a lot of points to something like that, where you're just saying, here's the answer. Okay? I know what sup means, I know what inf means. And then we'll list the first few terms of a given sequence. You had to do that in part 3, it's easy. And the ones that I graded, everybody got that. And then might be something about absolute values involved there, some statements with that. And we'll have some true-false questions. And then the last one will be proving something involving induction. And so I have, if it's okay with everybody, I'll just do some things that I've done in the past. Okay, so for an induction proof, here's 2 things that I've done in the past. Sir?
I don't know if I ever saw that side of the camera. I don't know if you want them to see this side of the form or not.
Did I not turn it? I don't know if I turned this here, talking about what was on the test. Thank you very much, Ash. Yeah, thank you. That's a good thing to do. Thank you very much. I'm going to make this comment. I hope I'm not saying anything bad, but, you know, people think different things. I taught a class where it was videotaped and there was no audience, ever. Okay? So it was a distance learning class and I do that. And sometimes the students complained because I would have sessions. I only did about 33 videos. I'd have some sessions where the videos were an hour and 20 minutes or something like that. And so they would say, well, the video was too long. But I didn't need 45 times, if you know what I mean. I knew it, so I made some long videos. And the way I felt about it was, well, if the video was too long for what you had time to watch, you could stop it. And so I didn't mean to say something smart, but that's what I was thinking. So I didn't. So here, when I showed the other side, I don't have to leave it there very long. They can stop. That's right. So I like that. Okay. All right. Having said that, let's do something here with induction. So prove. So this is an example. I've asked this in the past. Prove. Okay. I'm not sure I'm going to get the statement right. So prove that the sum is I runs from 1 to n of I squared is equal to n times n plus 1 times, I think it's 2n plus 1 over 6. I'm not even sure that's right. Okay? So I need a little time to look at that and make sure that it's right. And let's try something to see if it works. So when n is equal to 3, I'm going to come over to the side, check it out. So I'm not even sure that's right, if I wrote down the right formula. If I didn't write down the right formula, I'll do another problem. So when n is equal to 3, this is my check here. What is the sum as I runs from 1 to 3 of I squared. Well, I know b equal to 1. When I is equal to 1, we get 1 squared. Plus whatever we get when I is equal to 2, that would be 2 squared. Plus, okay, let's see. That's 1 plus 4 plus 9, that's 14. Now, when n is equal to 3, let's look at the other side. And if I get it, if I get the other side to be equal, I'm pretty sure that I didn't just make this up from memory. It's got to be something like that. So n times n plus 1 times 2n plus 1 over 6. Let's see. This is going to be 3 times 4, and then 6, 7 over 6. Let's see. This is going to be 12 times 7 over 6. That's 14. Because this is 2 times 7. It's 14. So that makes me convinced that this formula is correct, for my memory. But I want to prove it by induction. Okay? So I haven't proven it. I just wanted to verify that it worked for n equal to 3. Okay. That's our problem. Okay, so here we prove that this is true for each natural number. So I'm thinking the proof is by induction. And so how do we prove something by induction? Well, what we do is we must show the statement is true when n is equal to 1. Yeah. Okay, so what is it that I want to show? That is, show that the sum as I runs from 1 to 1 of I squared equals to 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Well, the sum as I equal 1 to 1 of I squared, well, that's just 1 being squared, which is just 1. Also, 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Let's see. That's equal to 1 times 2 times 3 all over 6, which that equals to 1. So, when n equals to 1, or so the statement, I ran from 1 to n of I squared, it does equal to n times n plus 1 times 2n plus 1 all over 6 when n equals to 1. We've proven that part when n equals 1, because we've got the same thing on both sides of the equation. Now, in induction, what do we do next? We assume the statement is true for n equal to k. And we've got to show that the statement is true for n equal to k plus 1. So assume true for n equal to k. That is, assume that the sum as I runs from 1 to k of I squared does equal, so I'm substituting in for n, the value k. It's k times k plus 1 times 2k plus 1 all over 6. We must show the statement is true for n equal to k plus 1. That is, we must show that the sum as I runs from 1 to k plus 1 of I squared is equal to, well, this formula, I'm going to look at the right-hand side of this formula, except I'm going to replace n with, that's right, I get k plus 1 times k plus 1 plus 1, that's k plus 2, and then times 2 times k plus 1 plus 1. That's 2k plus 3 over 6. That's what I got to show. I got to show that that's a true statement. Okay, well, let's take a look at left-hand summation. Note the sum as I runs from 1 to k plus 1 of I squared. What's that equal to? That's 1 squared plus 2 squared plus 3 squared plus all the way up to k plus 1 to b squared, right? Which I'll rewrite as 1 squared plus 2 squared plus 3 squared plus, what was the next to last term? That's what it is. Plus k plus 1 to b squared. Now the first k terms in this addition can be expressed as the sum as I running from 1 to k of I squared plus k plus 1 to b squared. And the reason that I wanted to do that was because I know, I'm assuming something about the sum as I run from 1 to k of I squared. I'm assuming I know what that is. What is that?
That's the thing we started with.
Yeah, it's equal to what? Tell me what to write down.
K times k plus 1 times 2k plus 1.
All over 6. Plus k plus 1 to b squared. Now to combine these guys, I'm going to have to get a common denominator. So this is equal to, one last step here, this is k times k plus 1 and 2k plus 1 times, plus, I should say, 6 times k plus 1 to b squared, all over 6. So we're trying to simplify that and trying to get what we're hopeful for. You know, I've erased what we were trying to get. Remember what we're trying to show is over here. I mean, this isn't part of the proof. Well, it was a statement we made earlier. This is what we're trying to get to. Okay, this guy is equal to, what was it, k plus 1?
K plus 2 is 2k plus 3. Plus 6.
That's what I'm trying to get. And I'm already working with that, okay? And I've got it to a certain spot. So this is equal to, from what we've previously written. Well, I want to tell you, if you look back to what we've previously written, you can factor out a k plus 1 from the two terms that are there. K plus 1 is a factor in both spots. So I'm going to pull that out. I'm going to have k plus 1. And when I factor that out, what do I have left? I've got k times 2k plus 1 plus 6 times what?
K plus 1.
All right. All over 6. So this is equal to k plus 1. Excellent. Here this will be, in brackets, it would be 2k squared plus k plus 6k plus 6. All over 6. And that's equal to k plus 1. Here I would have 2k squared plus 7k plus 6. All over 6. Well, it turns out that second expression in the numerator can factor. How do you factor? I don't know. 2k and then a k. And I think if you put a plus 3 here and then a plus 1 here, no, plus 2 here, plus 2. Let's see what happens. 2k times k is 2k squared. Here's 4k plus 3k, that's 7k, and there's 6. Yeah, that's the way it factors. All over 6. And that is what we were looking to get. So there it is. Is that okay? So by induction, if you want to make a conclusionary statement, say, so by induction, the sum as I runs from 1 to n of I squared does equal to n times n plus 1 times 2n plus 1 all over 6.
Every natural number.
Yeah, that's right. That's right. Well, you know, that's a problem that really isn't so related to our class, but it does give another example of induction. Where's another spot that in our class type of topics where induction could come into play? And I think that I might have shown this in class already, but here's something that we maybe have seen before, but it's a good place for induction hold true. You might say prove the absolute value of A1 plus A2 plus A sub n is less than or equal to the absolute value of A1 plus absolute value of A2 plus all the way up to absolute value of A sub n. And this is true for all n. Where A sub whatever is an element of R, I runs from 1 to all the way to n. We proved this by induction. Well, listen, this is really an extension of a very famous fact. What fact is it that I'm extending here? That's right, the triangle inequality. The triangle inequality says, hey, look, if you got two guys and you add them together, take the absolute value of that, that's less than or equal to the absolute value of the first guy plus the absolute value of the second guy. Well, here we're saying the extension is, it doesn't matter how many terms we're adding. If you take the absolute value of the addition, it's less than or equal to the absolute value of each number that was involved in the addition, added together. And so here, we do this proof, so by inductions, we would do it. And for n equal to 1, we'll note, so n is equal to 1. So on the left-hand side, we're taking the absolute value of n terms. When n is 1, we're taking the absolute value of just one term. So we have a sub 1. That's the left-hand side. Is that okay? Because n is 1. There's only one guy over there. Well, that's definitely less than or equal to, how many terms would you have over here inside absolute values? 1. So, I mean, there it is. So that's a true statement. That's good. Also, we have, for n equals 2, this isn't necessary to write down, but it's good to remind ourselves that a sub 1 plus a sub 2 is less than or equal to a sub 1 plus a sub 2, each individually inside absolute values, by the, what's the phrase I'm going to write right here? That's right. That's right. Good. Okay? Now we want to extend it. So how do we extend it? We say, well, we assume the statement is true for n equal to k. And I'm going to go a little slower here, so I'm going to say, what does that mean we're assuming? So we're assuming the absolute value of a sub 1 plus a sub 2 plus all the way up to a sub k is less than or equal to the absolute value of a sub 1 plus the absolute value of a sub 2 plus all the way up to the absolute value, the addition of the absolute value of a sub k. Yeah. What are we supposed to show?
Absolute.
Yeah, that's good, John. We want
The
to
absolute value of a sub 1 plus a sub 2 plus all the way up to
A sub k plus 1 is less than or equal to the sum of their absolute values.
That's what I want to show. That's right. That's right. Okay. Well, no, let's take a look at that left-hand side. The absolute value of a sub 1 plus a sub 2 plus all the way up to a sub k plus 1 can be rewritten as absolute value of a sub 1 plus a sub 2 plus all the way up to, what's the previous term? A sub k plus a sub k plus 1. And Dalvin, the reason I want to get a sub k involved is because, Brad, we know about the sum of the absolute values of the sum of a sub k's. Okay, so here, when I look at this first part and I look at this last part, so if you group the first k terms together, Audrey, Melissa, when I add a sub 1, a sub 2, up to a sub k, if you were to add them, it'd just be a number. So you can think of this as one number plus another number. Well, I know by the triangle equality, if you got two of them, the absolute value of the addition of two things is less than or equal to the absolute value of the first guy plus the absolute value of the second guy. But I know that the absolute value of the first k of them summed up together is less than or equal to the sum of the absolute values. That's what I'm assuming. And that's what we wanted to show. So that means that the absolute value of a sub 1 plus a sub 2 all the way up to a sub n is less than or equal to the individual absolute values added together. And that's true for all n element numbers. So that's a more typical type of proof where we use induction for the content that we're covering. And I don't know, I think we might have proven this in class, but I have not proven it in class at some points and asked it on tests. So I would ask, hey, can you do this in class? So it's something to be aware of. The next thing I'm going to do is I'm definitely going to give you one about the limit of the sequence, okay? And it's going to look something like what we had on homework. So let's do one of those together. Okay, so as an example of something that would be typical for me to ask, I might say, prove the limit as n goes to infinity. Let's do two examples. Let's say 3n plus 1 over n equals to 3. Now, this is a very good example. We don't have to do two examples. This is outstanding. Now, we might do it. Here's the proof. And let me say this to you. I'm going to write these words down in the directions. I'm going to say this using the definition so I'm going to write down epsilon k for a convergent sequence. So I'm not wanting you to use some algebraic property or anything like that. Let's just do it with epsilon k definition. So here's the proof. If I want to prove this, what's the very first statement in the proof? Yeah, that's right. And I want to tell everybody, I don't mean to say, oh, this board. That's what we say. If you write that down, you said something that's progressing towards writing down the correct proof, or a correct proof. So that's good. So look, the definition for a convergent sequence says, and if you know what it converges to, it says x of n will converge to x if no matter what epsilon, for each epsilon you give it, they're giving me one. I can't prove it for each individual epsilon. I say, just give me an arbitrary one. So you give me an epsilon. I don't know what it is. The only thing I know about it is that it is greater than 0. And what do we need? That's right. We need a k. Element of natural numbers, such that for all n bigger than or equal to k, the absolute value of the terms of our sequence, so 3n plus 1 over n, minus 3 will be less than epsilon. That's what we want. We don't have that. I'm looking for the k that would make that happen, if there is a k that exists out there. There will be. And so here's what I usually do next. I usually say, we want something to happen. We want the 3n plus 1 over n minus 3 to be less than epsilon. We don't have it, Dalvin. We don't have it, Melissa. We don't have it, Adam. I want that to happen. Okay? I want to simplify what I need to have happen. And then once I get this situation happening, I've got what I need. Okay, so we want, if I get a common denominator here, I think the common denominator is n. So we want 3n minus, no, it says plus 1. And then the 3 is the same thing as 3n over n. So I want this quantity to be less than, no, what is it? Epsilon. It's okay, everything's okay. So we want, here this is absolute value of 1 over n to be less than epsilon. That means we want, well, n is a positive number, so 1 divided by a positive number is positive. The absolute value of a positive number is itself, so we want 1 over n to be less than epsilon. I'm going to do another one, besides this example, but that's what we want. How do I know that I can get an n? Well, you know, I shouldn't even, that I can get an n such that 1 over n is less than epsilon. Well, go ahead. Well, really what we should do is we should solve for n. Let's get n involved. So we want, well, how would I solve for n? I multiply both sides by n and I divide by epsilon. So we want 1 over epsilon to be less than n. So I want my natural numbers, n, the ones I want to take, I want them to be bigger than 1 over epsilon. Well, how do I know that there's any natural number that's bigger than 1 over epsilon? By the Archimedean property. So by the Archimedean property, what do you mean by the Archimedean property? What do I mean by it? What does the Archimedean property say? Yeah, the set of natural numbers is not bounded above. What that means is 1 over epsilon isn't a bound for the set of natural numbers. What does it mean for 1 over epsilon to not be a bound for the set of natural numbers? Not an upper bound. That means that there's got to be a natural number greater than it. That's right, Brad. That's right. I'll say the right thing. There was this movie called What About Bob? You guys seen this movie? I didn't think it was too funny. But at one point in the movie, you can't remember the guy's name. The guy's name is Bob. He's been working with him for a good while. Anyway, it's kind of funny. There exists a natural number, we're going to call it k, such that k is going to be bigger than 1 over epsilon. So for all n bigger than or equal to k, look, if k is bigger than 1 over epsilon, and n is bigger than k, then n is going to be bigger than, right, 1 over epsilon. And that's what I need. That's good enough for me. Okay? Not every problem has 1 over n in it. Okay? And sometimes there's other things that are involved. Let us look at another problem. Kind of similar to this. So here is another problem. We're going to do it a little quicker. Essentially, the same type of problem. It says prove that the limit as n goes to infinity, let's say minus 4n plus 5 over, let's say 2n plus 6 equals to minus 2. You know what? Let's make a change. Let's make this 7. And then what it converges to is minus 4 over 7. That's what it converges to. It didn't even convert to minus 2. It had to change what it converts to. That's what's going to convert to. Prove this. Well, I know how to prove it. I know how the proof should start. How should the proof start?
Epsilon be greater than 0.
That's right, Adam. What are we looking for, Adam?
EAK.
Yes, sir.
So now we're the natural numbers. Such that for all n greater than or equal to k.
The absolute value of minus 4n plus 5 over 7n plus 6 will, minus a minus 4/7 will be less than epsilon. So what I'm going to do is I'm going to write down what we want. So what this means is we want the minus 4n plus 5 over 7n plus 6 minus, will be plus 4/7. We want that to be less than epsilon. I don't have that. Okay, that's my goal. Okay, so we want, simplifying this, I need to get a common denominator. The common denominator is 7 times 7n plus 6. So here, at the top, I have to multiply it by 7. And then plus, it would be the bottom of the second term's bottom would have to be multiplied by 7n plus 6. So better multiply the top by the same amount. We want that to be less than epsilon. I don't have it. Okay, John, I don't have that. But that's what is good enough. If I can get that, I'm in good shape. So I'm thinking, how can I simplify what I want? I want to put what I need to have happen in terms of something that we see is not so difficult to get that we can get based on an assumption. Or based on some previous work, previous facts. So we want, here let's see, what is this? This is absolute value. Minus 28n plus 35 plus 28n plus 24 over 49 plus 49n plus 42. We want that to be less than epsilon. So we want, simplifying that, well, the minus 28n plus 28n, that yields 0. So the top becomes absolute value of, what is that? It's 59, is it not? Over 49n plus 42. We want that to be less than epsilon. But now I can simplify this a little further. The reason I can simplify this a little further is the top is positive, the bottom is positive for every n. So positive divided by positive is positive. The absolute value of a positive thing is its self. So we want, I haven't got this, but if I can get it, I'd be in good shape. We want 59 over 49n plus 42 to be less than epsilon. Okay? So my goal here, I don't know that I've emphasized this enough, but I'm going to scream it. My goal at this point is to solve for n. That's what I'm looking to do. Solve for n. So we want, so I'm looking to solve for n. Let's see, I'm going to multiply both sides by 49n plus 42. I'm going to get 59 to be less than epsilon times 49n plus 42. And because that 49n plus 42 was positive, I didn't have to change the sign, change the direction of the inequality. Didn't have to, because we multiplied by positive. Then I'm going to divide everything by epsilon. And dividing by a positive number, epsilon's positive, I don't have to change the direction of the inequality. Remember, my goal is to solve for n. Look, this is what I need to have happen for n. N's got to be doing this. So we want, I haven't got it. We want 59 over epsilon to be less than 49n plus 42. I'm still trying to solve for n. So we want, if I can get this, I'm in great shape. 59 over epsilon minus 42 to be less than 49n. What am I going to do to solve for n? Divide by 49. So we want 59 over epsilon minus 42, all that divided by 49, to be less than n. Okay, So I want to make sure that my n's are bigger than this number. Well, how do I know that there's any natural number bigger than this number? By the Archimedean property, there's at least something out there that's bigger than it. This natural number. So by the Archimedean property, Archimedean, he was great. I knew him. There exists a K element natural numbers. I was talking to a colleague of mine today about China. He's from China, and we were talking about the differences countries, and China's a very old country. And I said, well, I was born in Greece, and in Greece they have a problem, and I imagine they have the same problem in China. The civilizations are so old. When they go to build something and they dig a foundation, they find something that's ancient Rome. I mean, you go to Greece and you just start digging, you find something. And if the museums or some kind of historical society says, wait, can't build here, you're in trouble, okay? Can't do this. Then they stop you. Okay? And so I've got a cousin who lives in Greece, Park Creek, and I got a cousin who lives in Greece, and she has this phrase, and the phrase is something to the effect of, we can't try to let the past live because the present has to live somewhere too. And so we've got to live somewhere. We can't just keep saying, oh, we can't build here, because there's nowhere we can build. Did you have a...
well, I actually had a comment to what you said.
Okay.
I went to Italy and they found a temple for Poseidon
Uh-huh.
in whatever the...
They stole that from Greece. Go ahead.
Anyway, no, they started digging it up and they're like, well, we can't touch this, we gotta get people down here. And...
Right. And so if you wanted to build something, they say, oh, no, you can't. Well, you can't build anything then, because there's something of historical value. Say,
Just throw the dirt back on and build on top.
yeah, exactly. But the problem is that you got to dig a foundation.
Just pour the concrete over it.
Yeah, that's the right thing.
Exactly.
Don't tell anybody. So there exists a K element natural numbers
There are no history majors here.
such that
Sorry.
59 over epsilon minus 42 all divided by 49 is less than K. So for all n big, I got that. Look, that's about argument. I got it. I was wanting something. I got to some point where that I wanted that I could get to. I can get that. And so for all n bigger than or equal to K, we have, not I want, we got it.
So that's it.
That's it. That would tell me, if I want to make the conclusionary statement, thus the limit as n goes to infinity. I've got the problem. What was it? Minus 4n
Plus 5
over
7 and plus 6.
equals to minus 4/7. That's it.
Is that supposed to be epsilon up there?
Here, so we have this guy's less than, no, is less than n is what it should be. Okay? That's what it should be. Thank you very much. No, it shouldn't be epsilon. I made a mistake. Thank you very much. Okay, so that's what I want to show you. I'm going to ask you one like this. 7 or 8 pointer, okay? You write this down, that's correct. The idea is that we can push far enough along in the sequence such that the terms of the sequence will be getting really close here. How close? As close as you want. What do you mean as close? You tell me how close you want. Okay? I want you to be within epsilon units. Okay, whatever epsilon you give me, I can get within that many units of minus 4/7 for this problem by pushing far enough along. How far along do you have to push? I have to push to 59 over epsilon minus 42 divided by 49. I've got to push bigger than that. If epsilon was something like 0.0001, I haven't got a calculator. Somebody got a calculator? If epsilon was equal to 0.0001, okay? Divide 59 by that.
590,000.
590,000. Okay. And I got a minus 42 from that. I think it's, yeah, 5. That's right. And then I got to divide that by?
49.
Yeah, I mean, so we're going to have to have a calculator, okay? So help me out. What is this?
12,039.96.
12,039.
Mm-hmm.
0.96. So what do I got to pick? K's got to be equal to 12,000.
39.
40. Is that okay with everybody?
Oh, it has to be a number.
Yeah.
Sorry about that.
That's right. Okay, got to be a whole number. But that's right, Brad. I like that very much. It's, what is K? The definition tells us it's got to be a natural number, okay? So the words are there for a reason. So that's how far along I have to go in the sequence to get with 0.0001 of minus 4/7. Okay? That's a long way out in the sequence. You say that's a long way, but the sequence goes on forever. So if you just go 12,000 steps and you got to go forever, you didn't get very far. Okay? So at some point from there on out, they're very close within 0.0001. The terms of the sequence are there. Those terms are very close to minus 4/7. Is that okay? So that's what that definition does. Okay, did anybody want to ask anything? Okay. Any problems that you want to see done? Anything?
So what do you mean by like true or false questions?
Just,
I could say something like this. Every convergent sequence is bounded. True or false?
False.
Every convergent sequence is bounded.
No, that's definitely true.
True. Okay, so I asked that question.
Can you make sure that one's on the test?
No, it won't be on this. Let A be a set such that the enthemum exists. Is the enthemum an element of A? Does the enthemum have to be an element of A?
No.
No. Okay. So things of that nature is what I will ask. Things like that.
Okay.
So those are just two examples. If I give you a constant sequence, if I say, let x of n be a constant sequence, then x of n diverges. True or false? False. False. Because it converges to the constant. Is that okay? Those are things that I could ask you. I could ask you this.
There's one question too. Some of my definitions got them from the book.
Yes.
Will those be okay? Do you
Yes.
want exactly. Okay.
Yes. If you write something that's equivalent, that's good.
Okay. That's,
So here might be another question I could ask you. The set of natural numbers is dense in R. True or false?
false.
False. There's lots of gaps between the natural numbers. I can find in the real number system 2 numbers that don't include in between them a natural number. You know, you look at -3 to -1. There's no natural number in there. Is that okay? The answer here is false. That could be something I ask. That's okay, for example?
Yeah.
Okay, well, we're going to have a study session on on Tuesday from 6:15 to 8:15 in this room. If you want to come by, I'll go over some proofs with you if you want, or more definitions. We went over definitions on Sunday, or I can go over statements of theorems if you'd like, whatever you'd like. Thank you very much.